In this video, we will solve another ice chart problem, and then I will give you one to practice. So here is a chemical equation, so carbon monoxide plus hydrogen in equilibrium with methanol, and we're given the initial concentration, so these are concentrations of carbon monoxide, hydrogen, and methanol. And our job is to figure out what are the equilibrium concentrations and what is the equilibrium constant. So in a problem like this, we have to start by writing out the change line, so we're already given the initial line, and the change line we're going to use x's to represent by how much the concentration changes. And looking at the stoichiometry, there's one carbon monoxide, there's two hydrogens. So every time the carbon monoxide is used up, there are twice as many molecules of hydrogen used up, so the concentration changes by twice the amount. And the methanol, every time one carbon monoxide is used up, one methanol is created. So we can write a positive x for here. So that's the secret to these problems, right? We don't know what x is, we don't know what the change is necessarily, so we write it in terms of a variable x. And at equilibrium, we can go ahead and we can sum the initial and the change. So this would be 1 minus 2x, and this would be x. And we're solving for x here, and in this problem here we can actually solve for x because we know that this value 0.15 is supposed to equal the initial value minus the change. And so if we want to find the change, then we can just go ahead and rearrange. So it is 0.5 minus 0.15, and that is 0.35. These are concentrations, so I should really write 0.35 moles per liter. And also, I am completely butchering significant figures just to make this problem a little bit easier. So if we want to know what the concentration now of hydrogen is, so the hydrogen concentration, we can go ahead and write this up here, is equal to 1 minus 2x. So we know what the value of x is. X is 0.35, and so that is 1 minus 0.7. So that is 0.30. And again, I'm recreating my significant figures and my units here at the end of the problem, which is a little bit naughty, so I apologize. And we can do the same thing for methanol. So CH3OH, that concentration at the end of the day is just x. And we solve for x. We said it was 0.35 molar. We want to know the equilibrium constant. So Kc is equal to the concentration of products at equilibrium. So notice we can't use the initial values over the concentration of reactants all multiplied together. But remember, whenever we've got a coefficient, we convert it into a power. And we now know what all of these are. So the concentration of methanol, that is 0.35. And remember, in these expressions here, we just use a number. We don't carry on the units. If you like the units, we're just divided out. And what else do we have? Carbon monoxide is 0.15. And hydrogen we solved for was 0.3, and we have to remember to square that number. And so if we plug all that in, we'll get the value of our equilibrium constant, which I get to be 26. Again, it's just a pure number, no units at all. So I'm going to go ahead and create a new slide and give you a problem to try, so hold on. So here's one for you to try. Here's the chemical equation up above. We're given the initial concentration of methane, of acetylene, and hydrogen. So we initially have no hydrogen at all. We're told the equilibrium concentration of acetylene is 0.035 moles per liter. So can you pause the video and use this information to fill out the rest of the table and calculate the equilibrium constant? So pause it, try it, and let's report back in a couple of minutes. All right, so let's have a go. So if you've unpaused it, we can go ahead and we can write the change line. So we know that there are two CH4s being used up in the problem. So there's a coefficient of 2 there, so we write minus 2x. But we are forming one C2H2, and we are forming 3 hydrogens. So our change line, right, is going to look something like this. At equilibrium, we essentially just sum together the initial and the change. And we can see that for the C2H2, that's already done for us. And 0 plus 3x is just 3x. So that allows us to find the value of x. So we know that essentially the initial value was 0. We add x to 0, we just get x. So we know x is 0.035. So that allows us now to calculate the concentration of CH4. So that is 0.115 minus 2x, so 2 times 0.035. And that ends up being 0.045. And again, we've played a little bit loose and fast with the units, so those should be moles per liter. And then 3x. So 3x is just 3 times by 0.035. And let's see, that is 0.105. And that should be a concentration, so it should be moles per liter. And now the last thing we have to do is find the equilibrium constant, Kc. So Kc would be the concentration of products over reactants raised to their stoichiometric powers. So 3 hydrogens becomes hydrogen cubed, 1 acetylene, C2H2. Okay, we just basically raise it to the first power, which is like doing nothing at all. And then on the reactant side, we got CH4, and we are squaring it. So we can just essentially plug in those values from above. So the hydrogen concentration was 0.105. Okay, we're cubing it. Remember, we're not using the units. The C2H2 we were told in the problem. And the CH4 we solved for. And we got to remember to square that. And if we put all that together, we get the equilibrium constant to be 0.02022 significant figures. Remember, it doesn't have any units at all. Did you get it?